Okay, hello? Okay, I thought hello, can anyone hear me?
Yes, sir.
Okay, I'm so sorry about that. I thought I ended meeting for everyone, and then I was trying to open it up, but then all of a sudden it's already there. Yeah, okay, so I think I'm in a much better spot right now. Sorry about that. Okay, let's get back to what we were talking about. Okay, let's calculate how far the car travels. So I can always choose my coordinates, which is easy for me to calculate. So I chose to put my origin at 0 at the initial position of the car. So I get x not to be 0. I can always choose my initial velocity of the car because it was stopped at the moment. So it was also at 0. So calculating the distance it traveled would be easy, right? You plug in the acceleration 2 meters per second square, you plug in time with 14, and you can soon calculate the distance the car travels would be 196 meters. Okay, so the answer for this one is C. So if we were to try to draw a plot of what's going on, right? So you have X versus T. So how do we represent the car? Okay, the car starts at 0, 0, right? And the car is accelerating. So you will draw a parabola. Also at T equals 14 seconds, right here, and the car had traveled 196 meters. So that's where the car is right now, okay? So, and then we wanna be able to finish the graph. So we also need to draw another one for the truck. So where was the truck? The truck was 100 meters behind the car to begin with, okay? So it will be somewhere here, negative 100. That's where the truck was at t equals 0. So, and the truck is traveling with a constant velocity of 14 meters per second, right? So you have to draw a straight line going across this. And then you might wonder, okay, at 14 seconds, where was the truck? So we can figure out where to put the line, right, at 14 seconds. So that's the next question is, how far does the truck travel during the same amount of time? Okay, so the truck, the physics of the truck is a constant velocity. So you will use v equals v naught and x equals x naught plus v naught times t for these two equations, right? These are for constant velocity. That constant velocity is 14 meters per second. And if I want to see the final position of the truck, right, I can plug in my initial position x naught and I can find the final velocity. Or I have another option. If I wanted to know the total distance, then I'll calculate this thing, whole thing instead. So that's really up to you what you want to do. Right, so if I wanted to do, okay, what is the total distance the truck traveled, I would just do distance equals velocity times time. So this is the velocity of the truck, which is 14 meters per second times 14 seconds. Again, it's also 196 meters. So it traveled 196 meters, but what is the position? The initial position of the truck is at a negative 100 meters. So it had gone from that point for another 196 meters, right? So it traveled 100 meters and then it traveled another 96 meters, right? So it will be somewhere here at 14 seconds. That's where the truck was. So if you finish the line for the truck, is something like this. So the truck, you can see it is approaching the car, but at 14 seconds, the truck is still behind the car. It has still had not caught up with the car. And from that moment on, the car will continue with that velocity for a straight line, right? Constant velocity and the truck will continue with this this straight line. So you can see that the car has a much bigger slope. So the car is always in front of the truck, and the truck can never catch up with the car. So before we do that kind of analysis, we can never say for sure whether they will catch up with each other. So we have to do this step by step. So after answering these two questions of the distance the car travels and the distance the truck travels, we know that the answer to the original question would be choice B, as we have mentioned previously. Okay.
Professor, so we got like pretty much the same answer, but I used 13.89 seconds because we rounded differently.
Yeah.
So I got like 192.93 and then 92 point, but for a test, that wouldn't really matter though, right? As long as it's obvious that the difference is because, for example, on your answer key, you rounded and I didn't.
Yeah, so obviously that would not matter. If it's a multiple choice in your test, I believe if you got 13.9, you would choose the 14 seconds. And if it were a formula entry type of answer, I will build the question so that it have some tolerance. So we'll have a few percentages of the difference to allow for the rounding errors. So yes, that obviously would not matter on the test. And thank you for asking that question. So I do have another modified example. I do not plan to go through this in class. I want to let you go ahead and do this at home, and then you can read my solution. Is if I were to let the car have a much smaller acceleration, then it is possible for the truck to catch up with the car now, right? So for example, the car's acceleration is 0.5 meters per square instead of the 2 meters per second square that we had. So in that case, they do finally catch up. And what you can do is you can make the final position of the truck equal to the final position of the car and calculate how much time it takes. Okay. And what's interesting here, I just want to point it out, you can look at the algebraic details later, is when you solve this quadratic equation, you'll get two different times. One is 8 seconds, 8.5 seconds, one is 47.5 seconds. So any guess on the meaning of these two different times? Would you say only one of them is physical, the other is not physical, we're gonna toss it out, or both of these time actually physically mean something? What do you think?
Well, so parabola, the car, if it's accelerating constantly, its position's basically like its distance from the origin or from where it started is moving parabolically. Like it's going in a straight line, obviously, but the distance could be modeled by a parabola, and then the truck could be modeled by the line. So a parabola can intersect a line in two places.
Okay.
It can do it in either 0, 1, or 2. And then I think earlier you were talking about like the analysis to figure out if they ever intersected. Wouldn't that be by using the quadratic formula and then looking at the discriminant to see if it's 1, 2, or 0 real solutions? Yeah,
so very good. A parabola, a straight line could intersect with the parabola at two different places. So for example, if you had, if your actual problem is like this, where this is a car, this is a truck. So what does these represent? So this will mean the truck is finally caught up with the car at this point, right? So you will choose 8.5 seconds to be the answer to the original question. But the second time also have some physical meaning, even if it's not what the question is asking, is here. What is the meaning here? So when the truck pass with the car, and the car might say, oh, we will meet again, right? So here they will actually meet again, meaning that they again occupy the same position. So eventually the car could also catch up with the truck, because the car is still accelerating. So it's still possible the car will catch up with the truck. So in that particular modified example, the truck and car will meet twice. The first time is the truck catch up with the car, and the second time is the car will catch up with the truck. So that's why you will solve for the equation, you get 2 different times. Which times you wanted to report at the answer depend on which time the question is asking you. Okay, so so you can see that simply by modifying this number, you will have a totally different type of problem they will actually meet. All right, so I see there are a couple questions. Sorry, are there any questions?
Sorry, if you have a negative time, though, we can throw that one out, right?
Yes, so when it's not physical, you have a negative time, then we certainly will throw that out. When it's a positive time, we want to think about, does it have any physical meaning? And in this case, it does. Most of the times has physical meanings. Okay, so let's see. I have a question. Will we have any multiple choice tests? Yes, your test will be a mix of multiple choice plus some numerical answer type of question. So you either will choose from A, B, C, D, or you will enter your answer. So it will be in those formats. The majority of your question will be the multiple choice format, but you can see the multiple choice will still, it's not just conceptual, it can be something like a calculational type of problem, like choosing from a list of numbers, in which case we'll have to do some calculation, of course. Another question is, can I please see the work for the question again for the first part? So I believe you're referring to this part, right? This is my work for the question for the first part, just to figure out how much time it takes for the car to reach the maximum speed. We chose the equation for velocity because that is that is the equation we will use. You want to find the time, you're giving acceleration, you know what the final speed is, so you can see that is a straightforward equation you wanted to go ahead and choose. So that is the question we left off from our previous class. And next, I wanted to introduce you guys to another type of motion, which is motion in the y direction. So constant acceleration in the vertical direction, right? So far we've been dealing with cars and motion that's in the horizontal direction. So what if you just put it in the y direction? Well, that's going to be very similar. And we can use all the equations we had derived previously. I want to let you know that I did post a derivation for this third equation on your canvas. You should already see it. It's really just by combining these 2 equations and you can find the third equation. So we're gonna use the same type of equation to solve for a free fall type of motion. So free fall is really just, so what is free fall? Free fall is really something that is free in the air, nothing is holding it. The only force, the only interaction that the object has is with the gravitational pull of the Earth. So that what we consider to be a free fall. So free fall is a special case for constant acceleration. So what we did in constant acceleration still applies, right? So for example, let's review a question you had previously answered in your pre-lecture. That's one of the bridge questions. Is if you were to find the distance traveled between t equals 1 second and 2 seconds. So this is for a ball rolling down a ramp, and it's also the lab you're going to do. I don't know, depending on your lab section, you're going to do a constant acceleration lab, maybe this week or early next week. It's also a constant acceleration. So when the ball rolling down the ramp, the ball is speeding up. The speed will increase in a steady way. So but then if you look at the distance it travels, it gets further and further. So how do you calculate the distance it traveled between 1 second and 2 seconds? So let's say at 1 second is here, and at 2 seconds it got here, right? So how do you find this distance? Well, by looking at this, you know that I know how much distance it will travel in 1 second. I know how much distance it will travel from the beginning to 2 seconds. So if I use this distance and minus the smaller distance, I will get the distance to travel between 1 and 2 seconds, right? So I'm gonna show and model how we do problem solving again is you are going to set your coordinates right here, where I'm going to set this at the origin where the ball is. And it seems to be, if I choose my coordinates to be along the ramp, it will be make sense instead of choosing something horizontal. So I wanted to choose my x-axis to be parallel to my ramp. I'm going to call that positive x. So that's just a little bit easier to label my position. And also the ball is initially at rest. So velocity initial is going to be 0. Velocity position initial is going to be 0 as well. That's my choice. So if I want to calculate the position of the ball at 1 second, I will use my kinematics equations. The t is 1 second, right? This is all 0, which is makes it easy to calculate 1/2 times the acceleration times time. So I wanted to see, okay, in order to find this position, I need to know what acceleration is. Before we study the forces, we don't know how to calculate the acceleration, but the problem does give us some more information. It does travel 1 foot between 0 seconds and 1 second, right? So I know, okay, so between 0 second and 1 second traveled 1 foot, that is 1 foot equals 1/2 a t1 1 second squared. So you can easily calculate your acceleration is 2 feet per second squared, right? So having that, you can do your second kinematics equations to calculate where the ball is at 2 seconds. So I'm going to do x2 equals x0 plus v0 t plus 1/2 a t2 squared. Okay, so I'm going to plug in 2 feet per second squared and multiply that by 2 seconds. So 2 seconds squared. So this becomes 4. So I get 1/2 and 2 cancels. I get 4 feet as the total distance it traveled from 0 second to 4 seconds. Right? So this is the position, which means if I were to look at the position, I will have 1 foot at 1 second, 4 feet at 2 seconds, right? That's the position. And the distance between first second and the second second will be 3 feet right here, right? So C would be the correct answer. You do have also the option of choosing 1 second as your initial position. It's not, you don't have to. For example, you say, okay, I wanted to look at the distance it traveled starting from 1 second. You can say, well, x2 is equal to x1 plus v1t plus 1/2 at squared. So in this case, this will be the position of the ball at t equals 1 second. This will be the velocity of the ball at t equals 1 second. And the total time from 1 second to 2 seconds is 1 second. You can see that 1 second had passed by. So you could do it that way. You can choose to evaluate your initial position to be whichever makes sense to you, right? And you can calculate the x2 minus x1 to be 3 feet. Okay, but I thought this would be a little bit easier. Excuse me. Because if I choose my initial position to be 0, 0, it's a little bit easier. So I simply just subtract my distance. All right, so free fall is not going to be anything new. It will be all these equations we have seen, and we apply it simply in the y direction instead of the x. So in terms of the free fall, let me show you guys something real quick.
Physics of Cartoons, Part 1. Law number 1. The character will remain suspended in space until it looks down.
So obviously in cartoons, this is a dramatic situation. We know that the physics is obviously wrong. The cartoon law number 1 is anybody suspended suspended in space will remain in space until they're made aware of its situation. Obviously, we know that is wrong. But sometimes in action movies, you will also notice some physical situations. By understanding more physics, you probably will be able to detect them much more easily when you see them again. I don't know if it's a bless or a curse. Maybe it will also make you enjoy those movies a little bit less, but nonetheless, it's a good idea to study the motion and understand why things go in different ways in different situations. The idea of free fall has been studied for many, many years. Back in the Aristotle's age, he didn't even have the correct understanding of free fall as we have to today. So his idea was the heavier object will fall faster. So someone wrote a sort of a poem to describe what Aristotle think about physics and how things fall. So in terms of free fall, Aristotle's idea can be described as such. There is a natural place for everything to seek as heavy things go downward, fire upward, and reverse to the sea, right? So it's a natural for a heavy object to go downward. So that is some observation we made many years ago. And in Aristotle's idea, if something is heavier, it's going to seek its natural place faster. So if you to drop 2 objects, one heavier and one lighter, the heavier would fall to the ground faster. Back then, people did not really have the idea of doing a controlled experiment. Right? That is fairly new. Before Galileo, people haven't really done this experiment to test the idea. You didn't know that people like you might think, well, I can just do an experiment to see if that's true. That comes very natural to you because we have been very familiar with the concept doing experiments, and we have learned so much from the accumulation of humans' history. So, and Galileo was teaching at the university at the time. So he wanted to test the Aristotle's idea, whether heavy objects seek its natural place faster. So the story often goes, I couldn't say this is exactly what happened in history, and the historians can't really confirm that's exactly what happened. But the general story goes that he dropped 2 objects from the Leaning Tower of Pisa in Italy. And then one is heavier and one is lighter. You would want to measure which one goes down to the ground. Do they fall and then take different time to fall to the ground? So very much to his surprise, that they do have a slight difference, but the difference is not big enough to justify that difference in their weight and difference in their density. So Galileo wanted to test the modified idea that maybe the speed will be proportional to its density. And density could be related to the weight of the object as well. But the result really surprised him. They differed by a small amount, and that amount could be caused by the difference in the air resistance. So it cannot be justified by using the idea of different density to explain it. So after doing many experiments, and later on people have done much more accurate experiment, we found out that it turned out to be, as long as we're all on Earth, any object will be falling with the same acceleration at the same rate. So which means if you release them from the same height, they will reach the ground at the same time. So that shows that they accelerate with the same rate. And we call that acceleration little g. That is the acceleration due to the gravitational pull. So you can call this the gravitational acceleration represented by little g. And by doing experiment, g is measured to be 9.8 meters per second square on Earth, roughly. Now, if you go to different places on Earth, you go to the equator versus if you go to the North Pole, different places will have slightly difference of your little g, but on average, we will say it's 9.8 meters per second square. And it's pointing downward always. So we can say our acceleration is negative if you had defined to be positive to be upward, right? Where your acceleration is pointing down. But little g is always a positive value, represent the magnitude of this acceleration. So if you want to put a minus sign on it, we would not say g equals negative 9.8, right? So that is wrong. G is always a positive 9.8, but you can write your acceleration to be negative g. So that is okay. All right, so that is what we found out by doing experiment, that all objects are subject to the same acceleration on Earth. And free fall is really just a particular type of constant acceleration. So we're not really learning anything new. The physics is still the same. So
Professor, sorry, could you go back up to the other slide for like 1 second?
here?
Yeah, thank you. I got the picture, thank you.
Okay, thank you. So when we say free fall, it doesn't mean objects have to fall to be falling down. As long as it's free in the air, it's called a free fall. It could be going up, and that still be considered in free fall type of motion. Free fall simply means your acceleration is down. It doesn't say anything about velocity. You can throw an object, it can be flying in a trajectory in the air, and that is still considered a free fall motion. It doesn't have to go down, straight downward. Okay. All right, so remember, if the object is free of any other interactions other than the interaction with Earth, the acceleration will always be 9.8 meters per second. So let's look at this question. If you drop an object in the absence of air resistance, now when we say object has an acceleration of 9.8 meters per second, we had already ignored air resistance. If you do have air resistance, obviously it will not be 9.8. So so the question would already tell you to ignore air resistance. If it doesn't want you to ignore air resistance, it will say so. It will tell you something about the air resistance. All right, so without the air resistance, what do you think the downward acceleration would be if you throw it downward versus release it from downward?
Is it like a poll, or do we answer you out loud?
Yeah, I'm looking. I don't know why my pool is not showing up. That's probably why when I come back, like somehow my screen was already there and the pool wasn't. Where's my pool? That's very strange.
Professor,
Yeah.
and you said it couldn't be negative, right?
And if it's a magnitude, and then it's always positive. If it's talking about magnitude. Okay, sorry guys. I don't know why my poll is not showing up. It's probably something goofy has to do with we got disconnected earlier. So if you could simply type your answers in the chat room, I would really appreciate it. If you don't want other people to see, you can send it to me so it doesn't have to type it to others. Okay. Okay, any other votes? We'll wait for roughly 10 seconds. Okay, so let me ask you guys this question. If you release a object and it falls to the ground, and if you throw an object and falls to the ground, do you think they fall to the ground with the same amount of time, or does one reach the ground sooner than the other? All from the same height.
So like dropping a baseball versus throwing a baseball from the same height.
Yeah.
I
Dropping
think-
it down versus letting it just release it down.
I'd say dropping.
Dropping. The one that you dropped from to the ground will reach the ground faster. So does that mean that they have different acceleration?
I don't think so, because if like you're throwing something downwards versus dropping it,
Mhm.
it's not like a rocket, because a rocket would have an acceleration extra to gravity, but that one's just that it has a different initial velocity.
It's the initial velocity that's different. It's
Yeah,
not.
because it's no longer, it's not being accelerated. It's just you got it to a certain velocity, and then once you let go, gravity's doing the rest.
Very good, very good. So I'm glad that we were not fooled by throwing it down, the information. So the acceleration is still the same, but that intuition that one will reach the ground faster is good intuition. So to reconcile with why do they have the same acceleration, we can think about this using our kinematics equations. Now, for example, if I were to say my ground is at 0, right? And I'm going to choose upward to be the positive direction, for example. It doesn't have to be, but let's just say if I do, and release it from the same height, h, right? So one object, you just release it, and the same object, or if you do it again, you have another velocity that is not 0, and they all will just fall down with the same acceleration, which is negative 9.8 meters per second. That's downward, right? So you can see that, okay, if I wanted to know the time it travels, I would go to my kinematics equation. So one thing that might throw people off, I just wanted to make it more explicit, is when we write our kinematics equations, it used this generic letter x, right? But x is just a variable. Right now, my variable is y, because all the motion is in the y direction, right? So x doesn't mean it has to be horizontal. X is just a variable, it's a placeholder. So I could just replace my x with y. Okay, let me share my screen again because it was frozen. So I can replace my x with y, and my initial height is actually going to be h, right? Because I was at a height before. So my initial height is at h. My final height is at 0, because eventually it falls down to the ground, right? So x becomes 0, x naught becomes h. Now, if v naught is 0, this terms goes away, and you'll have 1/2 negative 9.8 meters per second square times t squared, and you find your t. If you do have a non-zero velocity, right, v naught t minus 1/2 9.8 t second. So you will find this t, right? This t will be smaller than the other t. You'll find a different time, but you can see the acceleration is the same. The difference is your initial velocity, as some of you have pointed out earlier. Okay, very good. So I also wanted to show a graph representation, because it's always good to translate back and forth between different representations. We had just did some practice with doing the algebraic calculation, But if we wanted to put information on the graph, what would that look like? So let's say you're throwing a ball vertically upward, the ball moves up and then reach the highest point, eventually falls down. So if we wanted to draw the acceleration time graph and the velocity time graph, which pair is correct? So it's correct because you have to be consistent, right? So if your acceleration graph indicate you had chosen this to be positive, then it better reflect on your velocity graph as well. All right, for this one, I will have you have a quick discussion with each other for a couple minutes, and then when you come back, we can look at this together. I do understand that my voting is not able right now, but we can use our chat for now. All right, so I'll give you just a couple minutes to discuss this. You can do a screen share, do a snapshot of the picture before you leave to your breakout room. So you have your picture question in front of you. All right, so I'll see you guys in a couple minutes when you come back. All right, as people come back, please feel free to type up your answer in the chat. All right, I'm seeing a lot of choices for the second one. This one, right? Okay, so let me take a look at this one. This one shows my acceleration is negative. That I probably have chosen, which means I have chosen upward to be positive direction. So your acceleration is free fall negative 9.8 meters per second. And is that consistent with your velocity graph? You throw the ball upward first, okay? So that have a positive velocity to begin with. And reach a maximum height, which the velocity will be 0 at that point, and then going back down. So here you have a negative slope, right? Negative slope, which is consistent with choice B. Very good, very good. So my question for you, just one last question before we go, is if I had chosen downward to be positive, which I'm allowed to do so, right? Then I know my acceleration graph has to be this. So in that case, how would you draw your velocity time graph? So if you had chosen downward to be positive, how do you draw your velocity time graph? Anybody would like to share some thoughts with us?
So are you asking us like which of the 4 we would have picked?
And none of these 4 will be correct, actually. So how would you draw it? So if this is correct, how do you modify this so that this could be a correct answer? So I would say A is wrong, right? Not because this acceleration is wrong. It could be correct if you chose your downward to be positive, but it's wrong because these two are not consistent with each other. So if I choose downward to be positive, acceleration is positive, and my initial velocity is positive or negative. You throw a ball upward. So if my downward is positive, then upward will be negative, right? Yeah, so would be negative. Someone said reflect the velocity graph across the x. So I mean like kind of like this, but flipped, right? So you'll start with a negative velocity. Let's say if it's 5 meters per second, then it's a negative 5 meters per second, right? And it goes slow down to 0, and it falls back down, but now downward is positive. So it will be like this. And you have a positive slope, which is consistent as your choice for a positive acceleration. So if you got given this combination, that would also be a correct answer. Just so that we know that our choice for A and B has to be consistent with your implicit choice of which is a positive direction. Okay. All right. So that's all I'm going to talk about today for the free fall. I will touch upon the homework question. That is one homework that you will see in the second homework set. We will do that on Wednesday at the beginning of the class. But after that, we're going to switch to do some vector representations because we need to get ready to do our motion in 2 different directions. We have to know how to do vectors in 2 different directions. All right, I apologize for my unstable connection earlier. I like that we were able to finally make this work. And I'll see you guys on Wednesday. Bye, everyone.
Professor, sorry, what was wrong with B then?
Oh, what was wrong with B?
Yeah.
B is correct answer. B is not wrong. B is
Oh,
the
okay.
correct one. I'm just saying.
Okay,
if
sorry, I
we
thought
were-
you had
if
said
we were
all
to
of them were wrong.
modify A, then A could also be correct if we modify it.
Okay. Cool.
Yeah, thank you.
Thanks,
Thank you.
Professor.
No problem.
See you later.
See you. Bye-bye.
Bye.